All right, so we're going to do something called the comparison test. I'm going to call it the basic comparison test because in another section we're going to do another comparison test that's called the limit comparison test. So I want to make sure we're delineating between the two. Okay, so first off, these two series that I'm going to do the comparison test with, right, to compare, I have to have two. They both have to be positive terms. So no negatives. That means no like sine or a cosine, because sines and cosines go below, have positive and negative terms, right? So here's the deal. If this sum Bn converges and B sub n terms are bigger than A sub n terms, then the A sub n converge also. So the bigger converging gives us a good conclusion, right? The larger, if I compare the two, so I have to have a comparison between the two terms, and if the larger sum converges, I get that the smaller sum converges. If I have this B sub n diverges and B sub n is the smaller sum, then the larger one will diverge also. So the smaller diverging is good. And we kind of went over this with a whole bunch of pictures before. So again, positive term series, so it cannot be any negative ones in the sum. And I said no trig functions, but we have to make sure they're positive. So let's take a look at this. So what do I know about cosine squared? Cosine squared, right, if I was to draw cosine squared, it's always above the x-axis, right? Okay. Important fact, there's no squeeze theorem when we're in the series or infinite sums. No squeeze theorem. So that means only one inequality, right? We compare once, right? One inequality. Squeeze theorem has two inequalities, right? Okay, so I'm going to start off using the fact that cosine squared of n is smaller than or equal to 1. Okay, then I'm going to divide both sides by 4 to the n. Okay, so this is my first criteria. I've got two functions compared, and I know one of them is the one that's in my sum. So notice there's no summation marks, just like there were no integrals, right? When we did comparison test with integrals, there's no summation marks in here. So that's my first of my two criteria. Then I need to figure out what this sum does. So I need to put the sums back in, and I got to think about what is that? That's not p-test, that's a number to the nth power, that's geometric. And I can see, I don't have to write out terms, but I can see the A and the R are both going to be 1/4. So I can see this converges by geometric. So we are all on the same page. I don't need you to write out what the A and the R are equal to. We can look at it. I can look at it. So you just have to be able to identify that you see that it converges. So I have the two criteria. There's the one, there's the other, right? Two functions compared. This one converges. Double check, is it the larger converging? Is that the good? It is. So I get therefore, and you need to put the sum here. This converges also by basic comparison test. So this statement here with no summations, this statement here with a summation telling me why it converges by what test, and then a conclusion, and you have to have the summations here in the answer because you're saying this sum converges. All right, so let's look at this one. So this has to be positive, and let's think about it. Sine goes between 1 and -1, adding 3 to it, right? So sine is going to be smaller than or equal to 1. Sine of n plus 3 is going to be smaller than or equal to 4. So for sure this is positive. And then if I divide both sides by n to the 4th, okay, so there's my first of my two criteria. You don't need to number them. I was just trying to outline, kind of showing how I'm using the basic comparison test. That's the first step. Again, no summations when you're making this inequality. Next, I need to say what this sum does, right? So I need to have the n equal 1 to infinity on here. So what does this do? Well, this converges by p-test. Right? Oops, sorry, got messy there. This converges by p-test because I can see that p is bigger than 1. So what do I get as a conclusion? It's the larger, so the larger converging is good. So that must mean the smaller converges also by basic comparison test. Okay. Let's look at this here. A different kind of a problem. So let's just write down what I have here. And I'm going to compare it with the fraction without the number, right? So I'm taking this -2 off because I'm thinking that this can be written as 5/3 to the n, which looks like could be a geometric sum, right? If I'm looking at a sum. So which one is smaller? This has more in the denominator, so this is smaller, right? Now I'm going to be looking at the sum of 5/3 to the n and deciding what that does. I can see this is geometric, so this is a divergent geometric because r is equal to 5/3. You could also go do test for divergence on this, right? So you don't have to do both, but let me just write or t for d. If I took the limit as n goes to infinity of 5/3 to the n, since this number 5/3 is larger than 1, this equals infinity. So since not 0, this means it diverges by t for d. Okay, so this or this, one or the other, is this good? I have the smaller diverging. Is that good? Does that make the basic comparison test work? It does. So that means this one diverges also by basic comparison test.